All right, so today it's day 27, no, 37, I'm sorry. I'm gonna show what I did. Basically, I the other day I read a bit of this paper, like in general terms, and I implemented like a notebook that was part of the original code the author submitted, and I tried to adapt it because some scripts were done in R, but I mean, it's a bit messy, like a bit quite many functions, a lot of math, math formulas, and etc. So today I actually implemented like the simplest version of it, like a really um, yeah, a really small version of it, which is this notebook. I'm gonna just give a quick overview. I mean, all right. The paper. I'm gonna give first an overview of the paper. The paper is called a deep dynamic latent block model for the co-clustering of zero inflated data matrices. Okay, I'm gonna unpack everything that it's saying. But basically, it's you want to understand how it's dynamic because it's through time. It's deep because it uses deep neural networks. It is a latent block model because the way the cluster works, they work through blocks instead of individual like rows or columns. That's called co-clustering because it's a together like a relationship that goes together, and it's zero inflated data matrices because they're using sparse information. Okay, I'm gonna give a concrete example. So basically, we have some travels from one station from another. You have like some information that you have, I don't know, like you can think about it as different cities or different locations, and people take some routes from one location to another at different times along the day, and you can count the frequency of those travels, like when you are in one location and end up in the other location. And it's essentially a bipartite graph, which looks something like this. Let's say we have only 10 locations and 10 destinations, and every arrow represents like a travel from one location to another, right? And if we visualize this, this is essentially a matrix, right? But this is like a snapshot through time because it is at every hour of the day. So you can have like a matrix of, I don't know, in this case is 10 times 10 times 24, right? And this is just a toy data set because the actual data it's like 7,000 locations and many hours and okay, many different things, right? And this is just a toy data set. And the way the dynamical systems evolves is through a Poisson distribution. And the way we compute the Poisson distribution, instead of computing like the probability that this amount of events happen at this station, when this station is connected from station A to station B, instead of doing for each station, we do it by blocks. That's like the whole institution. So we sample the data and we intentionally create two periods of time. One, as we can see, like when you tend to go from this, like these stations tend to go from these types of stations tend to go to these destinations, right? So you have like, you can see that there are like these high like color blocks, and also the other time when they are like coming back home, let's say. So this expresses like a behavior. We want to understand this behavior to clustering, and this is a clustering that evolves through time. That's why it's dynamical, and also it's sparse because not every destination is connected, has always travels to all other destinations, but rather it's a sparse like type of information. And then like I plotted this. This is just for explaining the data, but essentially when you are like working with data, you don't know how the data relates. So it's essentially more like you have this matrix and the matrix is shuffled. So there is not exactly like a clean way to understand the clusters, right? And then after this evolves through times in a dynamical way, right? So you have, it's like a chicken egg question. you don't have, in order to know the trends, you need the clusters, and in order to know the clusters, you need the trends, right? So it's very difficult, I mean, in theory. So what we do is basically follow like some sort of algorithm, which is like essentially 3 steps. First, they initialize, they create. Okay, I'm gonna explain what they do. So basically, it has like 2 main components. One component is like the neural, let's say the neural network, which it estimates the dynamical modeling of the clusters through time. So it estimates the parameters, all right, of the Poisson distribution, of the block Poisson distribution. And the second component, it's called the E step and the variational step, which essentially is assigning like a probability of how well this, how much probability does this node has of belonging to this cluster at time t. That's essentially it. So you generate like a loss function and you optimize simultaneously both the clusters, like you understand which are the clusters, and you try to understand how does the information evolves through time, right? And optimize both at the same time, like a step by step, and they converge. That's essentially it. And yeah, I'm not gonna go in detail about the explanation, but as we can see in the end, when we plot the how does it evolve, how does it assigns probability to the raw clusters, because we have 2 types of clusters, the raw and the column clusters, we can see that when they have, we know that here it's very easy to differentiate the clusters, right, at when time is 8 and when time is 6. And aside from this, the clusters are more noisy, right? So it is reflected on the way the model assigns the probabilities. So at these types of probabilities, the probabilities are pretty much differentiated. Then it's a bit, they are not that quite clear, and then they get clearer away, and then it also is able to differentiate above the column clusters, right? And that's basically it. The code is in my GitHub.